is the solution to question number 7 for the 2014 Maths Methods examination paper. So for 7 part A, we want to determine t of this and give an example of a non-zero vector belonging to the kernel of this linear transformation. And then we want to determine R bases for the kernel of t and the image of t. And for part B, we want to show that the Cayley-Hamilton theorem holds for this matrix. So for 7 part A, the first part is very straightforward. We can see that A is -1, B is 0, C is 3, and D is 5. So we simply substitute for A, B, C, and D, and that gives us this cubic polynomial. Now we want to find a non-zero vector which is in the kernel. So we need to find an A, B, C, and D which gives us the zero polynomial. Now if you take t of 1, 1, 1, 1, so A, B, C, and D are all 1, then you can see that 1 minus 1 is 0, so the coefficient of x is 0, C minus A is 0, coefficient of x squared is 0, and D minus A is also 0, coefficient of x cubed is 0. So t of 1, 1, 1, 1 gives us the polynomial 0. So therefore the vector 1, 1, 1, 1 is in the kernel of this linear transformation. Now to find the bases for the kernel and image, let's take the image first of all. So t of this matrix gives us this polynomial. So that means that the image of t is spanned by x, x squared, and x cubed. These vectors are linearly independent because a times x squared plus b times c x squared, a times x plus bx squared plus cx cubed is 0 implies that a, b, and c are 0. So therefore x, x squared, and x cubed forms a basis for the image of t, and the dimension of the image is equal to 3 because we have three non-zero vectors. For the kernel, we want to know which elements map to 0. So we need to know which polynomials here give you 0. And you can see that this polynomial is 0 when a equals b equals c equals d. Now when a equals b equals c equals d, then the matrix is equal to 1, 1, 1, 1 because all of the a is b is c is d. So we only need one constant there. So therefore this single vector forms a basis for the kernel, and because one vector on its own it has to be linearly independent, then this forms a basis, and the dimension of the kernel is equal to 1. For part B, the Cayley-Hamilton theorem states that a matrix satisfies its own characteristic equation. So if we find the characteristic equation, so we subtract lambda on the diagonal, find the determinant, and this is the characteristic polynomial, and then we set this equal to 0, and that gives us the characteristic equation. So if we, instead of lambda now, we substitute the matrix A. So here is a squared minus 4a, and then take away 8. There's no constant, you can't really just have minus 8 as a matrix, so we multiply this by the identity matrix. And if you work out all of this, then we do get 0, 0, 0, 0, which is the 0 matrix. So therefore this matrix does satisfy its own characteristic equation. And that concludes the solutions for question number 7.